This video will cover the basic idea of using partial fraction decomposition to integrate rational functions. Okay, so the main idea here, the overarching thing is if you have a rational function, a complicated rational function, you can break it up as a sum of simple things, simple rational functions that we know how to integrate. Now, what's a rational function? Remember, that means just some polynomial over a polynomial. So things with just x to a power, a bunch of that added up, multiplied times constants. There's no radicals, there's no trig functions, there's no natural logs or other logs or exponentials, there's no inverse trig, there's no hyperbolic. It's just like the very easiest stuff, only you have one of them over the other one. Okay, so what do I mean by simple ones, right? I'm turning a complicated rational function into a sum of simple ones. So there's three basic types of simple rational functions that we will deal with. There's a constant over a linear function, a constant over an irreducible quadratic, and a linear over an irreducible quadratic. Irreducible quadratic just means you can't factor it. So if you can factor it, we'll break it up and just get linear things on the bottom. Okay, so one at a time, let's see what you do with these, with an example of each. So for a constant number over a linear function, that's the simplest case, it looks something like this. A number over something where the highest power of x is just plain old x, so like 3 over 2x minus 1. Well, what's the integral of something like that? You can factor the constant out, so we can think of these always as just being 1 over a linear function. And those are always going to be some kind of natural log. Anything that's just a power of 1 in the denominator will be a natural log. And don't forget the absolute values, but unfortunately this isn't quite right. If we took the derivative of this, we'd have 3 times 1 over that 2x minus 1, which is great, but we'd also have to do times 2 because of the chain rule. The derivative of the inside is 2, and we don't want that. It's not there in the integral, so we have to divide by the 2 so that the derivative works out to be what we want it to be. And don't forget the plus a constant. Okay, so that's the integral of a constant over a linear will always be some kind of natural log like this. You can use u substitution if you want with u equals that denominator. Get the same answer. Okay, what about a constant over an irreducible quadratic? So as an example, a number like 4 over x squared plus 9. The way you know you can't factor it, the way you know it's an irreducible quadratic, is if you try to use the quadratic formula, you'd get imaginary stuff. Or in other words, it's something squared plus a positive number. So it'll never hit 0. It'll never be negative, so it never crosses the x-axis, so it can't have any factors, can't have any zeros of that polynomial. So x squared plus 9 is a good one. Can't be factored, doesn't have any numbers that make that equal to 0. So what do you do when you want to integrate something like that? Well, this is where, well, first you factor out the constant, so we can always assume the numerator is a 1. And I'm going to write that 9 as a 3 squared. And it turns out that's the antiderivative. That 4 stays. And then the 3 shows up in these denominators, and you might be wondering, where on earth did that come from? Well, if you look at what we're integrating, 1 over x squared plus 3 squared, it's almost like 1 over x squared plus 1, right? That would be an arctangent. The integral of 1 over x squared plus 1 is arctangent of x, so there's this modification that has to happen. You can do that every time it comes up using a trig substitution, so that would be a tangent substitution. Or this one comes up a lot in these, so you might just want to memorize or have it available for reference a lot, this formula. It will be on the handout that you get. So 1 over variable squared plus number squared, the integral of that is 1 over the number times arctangent of the variable over the number plus a constant. Okay, so that's the second kind of quote-unquote simple rational function. And then the third one, a linear over an irreducible quadratic. And we'll deal with that later. You split it up and use a u substitution on one piece and the previous thing with the arctangent on the other piece. I advise you to read some examples in the book to see that in action. Okay, and notice I said these were simple. These don't look all that simple, but trust me, they could be much worse. So these integrals are the three main rational functions that you need to know how to integrate. Everything else we're going to break apart into these, all added up. Okay, so for example, these guys are simple in that if I had something like this, 1 over x plus 2 over x minus 1, and I want the antiderivative of that, that's easy based on what I just did. First of all, with sums, you can split it up like so. And then the first one's a natural log of the absolute value of x, and I have 2 times the natural log of the absolute value of x minus 1 plus a constant. Great, but the problem is the integral won't always come presented so nicely. For example, those two fractions added together, well, we can actually add the fractions and get another way to write it, right? So what do? You want a common denominator. Our denominators are x and x minus 1, so the common denominator will be the product, x times x minus 1, which means I need to multiply that fraction to get the x minus 1, and I need to multiply the other one to get the x in there. So that first fraction becomes x minus 1 over x times x minus 1, and the second fraction becomes 2x over x times x minus 1. Now that they have the same denominator, we just add the numerators. 3x minus 1 over x squared minus x. So that's the same thing as 1 over x plus 2 over x minus 1. But what if the integral I was handed was this? It's exactly the same. If I knew I could break it up as 1 over x plus 2 over x minus 1, it would be really easy to do. So the question is, how can I tell that this thing, 3x minus 1 over x squared minus x, actually is equal to this sum of simpler fractions? We need to find a way to go backwards. Find the two simple fractions that added up to give me this one. Once I find those simple ones, I can do the integral easily. So I'm going to show you the procedure here. We'll see it more in class. I really encourage you to read the book. But that's the goal of partial fraction decomposition, is to take one of these fractions that's not simple and think of it as what simple fractions add together to give this one. Right? There are some general rules in the book and on the handout that I've tried to summarize on the handout. You'll see. It looks a little complicated, but there are general rules. And then there's also sometimes that you need to do a polynomial division. If you need to do that and you don't know how to do it, there's another video that I've made. Okay, let's go back to our example. We have 3x minus 1 over x squared minus x, and we want to think to ourselves, that's not a simple one, right? That's not a constant over linear. It's not a constant over irreducible quadratic. It is a linear over quadratic, but that denominator is not irreducible. I can factor it. So it's not any of the simple forms. So that means I want to break it up into simple ones. 2 or more simple fractions, simple as defined on the first slide, added together to give me this one. Okay, so how do we do that? Here's our fraction again. Oops. That's supposed to be an x squared minus x there. Let me just fix that. There we go. All right. So the first thing we do is we factor the denominator. Right? I happen to know that x squared minus x is x times x minus 1. The reason I factor it is that tells me the denominators of the simpler fractions that are going to add up. So here's what I'm going to get eventually. And now I know that the denominator of one of them is an x and the other one is an x minus 1. Again, the general rules for this are going to be in the book and in class. Okay, well, let's call those numerators names, a and b. So I've got a over x plus b over x minus 1, and those are going to be numbers, and I need to figure out what numbers they are that make this add up to the fraction I want. So to figure that out, I take the equation I've got over there and multiply through by that big denominator, x times x minus 1. So I'll multiply on the left, and I'll multiply on the right. What happens? On the left, the denominator completely cancels with the x times x minus 1, and I just have 3x minus 1. On the right-hand side of that equation, I've got two pieces. The a over x times x minus 1, the x's cancel, and I just have a times x minus 1. The second term, b over x minus 1 times x minus 1, the x minus 1's cancel, and I just have b times x. Okay, that may be a slightly nicer equation to work with, but what good is it? Well, I can substitute in different values of x, whatever values I want, to find a and b. The idea is this function 3x minus 1 should exactly equal the function a times x minus 1 plus b times x. So whatever value of x I put in needs to make that true. For example, if I decide to plug in x equals 0, on the left I have 3 times 0 minus 1, and on the right I have a times 0 minus 1 plus b times 0. That pretty quickly simplifies to negative 1 equals negative a. So a equals 1. If I pick a different value for x, for example x equals 1, I can substitute that in and get 3 times 1 minus 1 equals a times 1 minus 1 plus b times 1, which gives me 2 equals b. So I've found my numerator and denominator. Yay! Now I know that the numerator of the fraction with x on the bottom is 1, and the numerator of the fraction with x minus 1 on the bottom is 2. So I've gone backwards. I have started with 3x minus 1 over x squared minus x, and I have realized that that is equal to 1 over x plus 2 over x minus 1. That means if I want to do this integral, I can replace the complicated rational function with the sum of two simple ones, and as we saw before, those are antiderivatives we know how to do. Okay, let's go back now and look at all that stuff we did on the couple of slides ago to decompose this, and yeah, hang on, I need to fix that. Yeah, so the first thing we did was factor the denominator, realize that that lets us write down a sum of fractions with those denominators, multiply through to clear out the fractions, and substitute in different values of x to find our numerators. Okay, so I can break this down into sort of the overarching theme. You factor the denominator, use the knowledge of those factors to find the partial fraction form. So here each of those factors of the denominator was the denominator of one part of this partial fraction form. And then this multiplying through and substituting values of x is just, we're finding those numerators. So we factor, we find the form, which includes the denominators, and then we find the numerators that go with those denominators. And that's how we break up a complicated rational function into a sum of simpler ones. In the examples in the book and in class, you'll see the rules for that form part, exactly what the denominators should be, what kind of numerators each one should have, etc. It gets kind of complicated, and we'll see more examples. I hope you get a chance to read the book before class. The more you can see of these examples, the better. I will see you then.